Hi, welcome to part 3 of the lecture on conditional probability. In this lecture, we are talking about the multiplication rule. So this is how the multiplication rule is stated, as you can see here, right? And this is just a rearrangement of the conditional probability formula that we've been talking about. If you just look at it, this is probability of A given B equals probability of A and B over probability of B, right? So the multiplication rule is actually more useful when we are looking at an experiment that consists of several stages in succession, right? So the conditioning event, for example, B in this case, describes the outcome of the first stage and A the outcome of the second, and so on. So we'll see at we'll look at a couple of examples to better understand this, because sometimes you're interested in probability of A and B when we already know probability of A given B, or when we are able to find out what is the probability of A given B and we are able to find out what is the probability of B, right? Let's look at an example to understand this. Okay, 4 individuals have responded to a request by a blood bank for blood donations. None of them has donated before, so their blood types are unknown, right? So suppose only O positive is desired and only one of the 4 actually has this type, right? So we are typing each person out of the 4 and we know that only one of them has it, right? So if the potential donors are selected in random order for typing, what is the probability that at least 3 individuals must be typed to obtain the desired type? Okay, if we pay a little attention to the way the question is framed, we are trying to find out the probability that at least 3 individuals must be typed, which means to obtain the desired type, which means somehow the first 2 should not have the type O, right? If you think about it, this is what this problem is stating, right? So let's say B is the event, I'm writing the event, that the first person typed or first type is not O positive, right? So I can find the probability of B, right? So out of the 4 people, if I choose one of the 3, that's the first type is not O positive, right? So that's the probability of B actually, right? Okay. Now, the first is not O positive. We also need that the second one is not O positive. Then only we'll arrive at the probability that at least 3 individuals must be typed to obtain the desired type, which means 3 or more, right? So that means I need to have another event A, which means second is not O positive, right? Okay. So now we don't need the probability of A, but we need the probability of A given B here. Why? Because we are interested in the probability that at least 3 individuals must be typed, which means that already the first one should not be O positive, and given that the first is not O positive, the second one should also not be O positive, right? And finally, we are interested in at least 3 are typed before we obtain O positive, which means we're interested in probability of A and B, right? So what we require is probability of A and B, like both the first and the second are not O positive, right? And in order to arrive here, I know that there is this experiment that will go on in succession, right? And so I can figure out this, which is now I have like 3 remaining people and 2 of them will not have this O positive type because that's the information that's given to me, right? Okay, so what I need is the probability, let me rewrite it, at least 3 are typed before we actually get the person who has the actual O positive, which means that I'm interested in probability of A and B, right? And then by the formula of the I wouldn't say conditional probability right now, but the multiplication rule. So by multiplication rule, right? This is probability of A given B times probability of B, right? So I can plug in the values. I already have the values, which is 2 times 3, 3 times 4, which is 6 over 12, which is 1 over 2, right? Okay, so let me reiterate what I already said about the multiplication rule, which is that the multiplication rule is most useful when the experiment consists of several stages in succession, right? The conditioning event B will describe the outcome of the first stage and A will describe the outcome of the second, just like we saw in our typing example, right? So that the probability of A given B, conditioning on what first occurs, will be known, right? And then finally, this rule is easily extended to experiments involving more than 2 stages. Now let's look at that. What does that mean? So for example, I'm interested in 3 different things, probability of A1 and A2 and A3. So the way we can expand the existing formula is that the probability of A3, so if we know the probability of A3, given A1 and A2 have already happened, and I already know the outcome of this and this, right? So I can expand this. And if I further expand these two here, I'll get something like this, right? Which is, so how do I find this term out? Again, I'm applying the multiplication rule, which states probability of A2 given A1 and then given A1 has occurred. So I should be able to figure out probability of A1 first and then A2 given A1 and then A3 given A1 and A2. And I know how to find that out, right? So A1 occurs first, followed by A2 and finally A3. So I'm just expanding on what we already said in our previous problem, right? So this is the more generalized form of the multiplication rule. Okay, so for example, expanding on what we already saw in our first example for the blood typing experiment, what happens if we are interested in the probability that the third person is O positive, right? So let me write it down. I'm interested in the probability that the third type is O positive, right? Now I can utilize the multiplication rule here because I'm interested in the probability that the third is O positive, right? So I'm just like writing third is, given that first is not and second is not, right? Because only one person in the entire group actually has it, right? And then we're interested in that probability times, and I'm by the way using the multiplication rule here. Second is not given first is not, right? So this is in succession, given first is not times the probability that first is not, right? Because we began from first and then second and then third is, right? So first is not, then only third is possible, right? So every successive step is based on the condition that something happened in the step before, right? So I can just go ahead and plug the values. I know them from my experiment earlier. So so this is something that we found out, right? So that's why it was 1 over 2. And then we also figured 2 over 3 probability of A given B, right? And then we also figured probability of B, which was 3 over 4, right? So if we just solve this, this is 1/4 or 0.25. Okay, so that's the multiplication rule. Let me see. Let's talk a little bit about sampling bias and also transposed conditional, and then I'll finish this video, and in the next video then we'll discuss the Bayes theorem. Okay, so what is sampling bias? Now we've been looking at, when we were talking about conditional probability and the multiplication rule, we saw all these terms, right? Probability of A, probability of A given B, probability of B given A, and this thing, right? The and probability of A and B. Okay, so be extremely careful while using like any of those terms, and one should not be replaced by the other, right? For example, especially like I'll try want to emphasize on this. because this happens many times, using probability of A instead of probability of A given B. If there is certain extra information available to you, utilize that. Or if that extra information is not of significance, then do not utilize that, right? For example, and this is unknown, you might want to go back and Google this. Dewey defeats Truman. This had the results of US elections skewed, so you should go and check that. But a small example would be that let's say I'm interested in the probability that a voter will vote for the Republicans, and that's like around 0.12. If I ask Apple to call up all iPhone users to see how they will vote, this probability will have a different value than 0.12. Why? Because I am basing my entire survey, so to say, on that the voter has an iPhone, right? And so this is not the right number that I'll get if I'm doing my survey using some condition, which in this case is the iPhone users only, right? So this is why, which is why we have to be extremely careful when using probability of A instead of probability of A given B, right? So understand that if I'm getting at a certain number, it's given, or is it based on certain bias or not, right? So I'll get this biased value because I'm basing my survey on iPhone users only, on the outcome of iPhone users only, right? And which most likely will have a higher number than what I thought it should be. So that's what sampling bias is. And another issue that comes up while we are framing our solutions is the transposed conditional. Understand that the probability of A given B is not equal to the probability of B given A. That's a big confusion, right? For example, the probability that it is cloudy outside given that it's raining, right? So probability that's cloudy given raining, and then probability that it's raining given cloudy are not the same thing. Just think about it, right? So these are not equal, right? So this example is easier to understand and visualize. And based on this example, you should be extremely clear while you should take extreme care while framing either this or this and understanding that these are not equal. Okay, with this I end this video. In the next video, I'll talk about Bayes' theorem and the law of total probability.